In this video, we're going to look at how to graph polynomials and how to write the equation of a polynomial. So the most basic way of graphing a polynomial is the same as any other function. You can just make a table of values, check some inputs, check some outputs, and then plot the points. So this table, we can see we have 5 xy coordinates that are plotted on this graph over here. You can say that we make our cubic function x cubed, and it looks a little something like this. But the question is, how can you make sure that you get enough points in your table to actually capture the behavior of the function? And with like a computer, like a Desmos software, you can plot really as many points as you want almost instantaneously. But if you're doing this by hand, we want to consider a couple of key features with polynomials. Okay, so one of the tough things is figuring out, where does the graph change directions? And the first most important thing to think about is the end behavior of the function. What happens as x goes to infinity? What happens as x goes to negative infinity? Then we want to think about the domain and range. The domain for all polynomials is all real numbers. The range can either be all real numbers or there can be some sort of range restriction. Then we want to think about, does the polynomial have any maxims or minimums? It could have absolute maximums, for example, like a parabola, or I should draw a maximum, and an absolute minimum. So that's like an example of the highest point the function will ever get to, or the lowest point it ever gets. Or it could have a local or relative one. So if I have something that looks like this, this is a local or relative max. It's not the highest the function will ever get, but it does count as a relative maximum or relative minimum. And it's kind of like the turning point. Here we would have a local min. Actually, for this function, it would also be a global min, it looks like. And then here we would have a local min as well. And any type of function that's a polynomial can have these. So I could have a function that looks like this. And here I'd have no global max or mins because the function's going to infinity at the ends. But here would be local maximums or relative maximums. And here we would have some local minimums. Okay. We can think about what intervals does the function increase or decrease on. So with that example we just looked at, we go up, down, up, down, up, down, and up. Again, that has to do with our turning points. So we basically change direction every time we hit a max or a min. And then the really important one here is the intercepts. And for our purposes, between end behavior and intercepts, that's really how we can sketch our functions. So the x-intercepts are really, really important, and then the y-intercept gives us another point to work with. So let's take a look here. First, we're just going to take a look at some graphs and try to describe them. So if I look at the function f of x equals x squared minus x minus 2, see that this is a quadratic trinomial. The domain of all these functions is all real numbers. The range, looking at the graph, we see we have a global or absolute min at 0.5 comma negative 2.25, sorry. So negative 2.25 to infinity. Our in behavior as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x also goes to infinity. Our y-intercept, tough to see. It looks like it's at 0 comma negative 2. So we're going to make that assumption here. The x-intercepts are at negative 1, 0, and 2, 0. We have a global, or I'm going to write absolute just to mix up the vocab, minimum at 0.5, comma negative 2.25. And then we are decreasing on the interval negative infinity to 0.5. We remember we described these based on the x intervals, and then we are increasing from 0.5 to infinity. And that describes our function. Now that's just a quadratic, but all the polynomials basically follow this. All the even degree polynomials with the highest power that's an even number are going to have matching end behavior. So they will both finish up or they will both finish down, both ends of the graph. The odd functions will look a little different. But our second example here has another even function, power of 4, and we notice that we finish with the same end behavior in the down direction. Domain is all real numbers here. Range, looking at our graph, I see my maximum is at 0.75, and we go down to negative infinity. That's inclusive. Check that I did that before, yep. End behavior, so as x goes to negative infinity, f of x is also going to negative infinity, and as x goes to positive infinity, f of x is going down to negative infinity. So when we have an even power, the outputs will be doing the same thing, whether we're going to negative infinity or positive infinity for the inputs. Y-intercept of this function is 0, 0. The x-intercepts are negative 1, 0. We have 0, 0, and we have 1, 0. And one thing I'm going to add here, we will cover this a little later in the video, but this is going to have a multiplicity of 2. And I can tell that because this graph bounces off the axis there. And we'll look at that a little bit more later on, but that tells me there's a multiplicity of 2 because it doesn't actually cross the x-axis. I have two maximums. Now, they could be referred to, I guess, as global or absolute maximums or relative maximums. It's a little odd that there's two of them. So I'm just going to write max at negative 0.707, comma 0.75. Now, I'm pretty sure 0.7 is the square root of 2 divided by 2. But we don't actually know, and it's just a decimal approximation. So I'm going to just use the decimals here. So these are our maximums. And then we are increasing. So from negative infinity to negative 0.707. Then we go back, and I'll highlight this. We're increasing, then we decrease from that x-coordinate, negative 0.707, to the x-coordinate of 0. Then we turn around, bounce off that axis, and increase from 0 to positive 0.707. And then finally well, I actually should be writing this differently. So we increase on those two intervals. Oops. Maybe I'll use the little U symbol for union. And the other ones we are decreasing. I got a little ahead of myself. Decrease on this interval. And we are also decreasing on the interval at the end here. All the way for infinity. So 0.707. Okay. That looks good. Okay. Let's look at one more here. We have 2x cubed minus 2x. So my domain here is all real numbers. My range is going to be all real numbers. So anytime this is an odd highest degree, like a cubic, a quintic, seventh degree, the range and the domain are both all real numbers. End behavior is going to be opposite this time. So one end of our graph is going to be going up, one will be going down. So we can say as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x also goes to negative infinity. So we can see that the end behavior is opposite on different sides of our graph. Maximum and minimums here. We can see we have a max, it's a relative or a local max at negative 0.577, comma 0.77. We have a relative or local min at 0.577, negative 0.77. Okay, if we look for intervals increasing and decreasing, from left to right as we read it, our function increases, and we're describing the x intervals, so from x coordinates of negative infinity to negative 0.577. We are increasing. We can also see that we are increasing on this interval here. So we can say from 0.577 to infinity. Describe the x's. Then we are decreasing in between. So we can say we are decreasing from negative 0.577 to positive 0.577. All right, the y-intercept. Well, we can see that's at 0, 0. The x-intercepts, we can see from the graph, we have at negative 1, 0. We have at 0, 0. We have at 1, 0. Okay, and that fills out our function. Another odd function here, x to the 5th minus 5x. So the domain is all real numbers. Range, it's an odd highest power, so we're going to say all real numbers. End behavior, one side ends up, the other side ends down. So this time we can say as x goes to negative infinity, f of x goes to negative infinity, x goes to positive infinity, f of x goes to positive infinity. Okay, so kind of matches the other one. We have some relative maxes and mins. So here we have a min, here we have a max. Using the graph, we can say that our relative max is at negative 1, 4, and our relative min is at 1, negative 4. Very nice symmetry. If we look for the x intervals over which we are increasing or decreasing, we can say that we are increasing on these two intervals. So increasing from negative infinity to negative 1, and also from positive 1 to infinity. Then we are decreasing between those. Polynomial is continuous, so we decrease between negative 1 and 1. And I personally don't include the actual coordinate because I say at that point it is neither increasing or decreasing. You can kind of say either one. Y-intercept is at 0, 0 again. X-intercepts, these are not quite so obvious from the graph. I guess they are labeled, so we have that going for us. So we can say negative 1.495, 0. We have 0, 0, and we have 1.495, 0. Got a little excited. I thought we were going to get to actually factor and solve. If we had factored our polynomial up top, we would get x, or x times x to the 4th minus 5. Then solving that, we would get x equals 0, and then x to the 4th minus 5 equals 0. X to the 4th is 5. X equals plus or minus the 4th root of 5. So those are actually what these decimal approximations are supposed to represent, but decimals are fine, I guess. Okay, so some key things to note. The domain of polynomial functions is always going to be all real numbers, negative infinity to positive infinity. Because of that, there will always be exactly one y-intercept, and it occurs when x is 0. The reason being is if our domain is all real numbers, well, that means at some point we have to cross this y-axis. There's no way to have all real numbers but not be defined there. Additionally, because this is a function, that means it only crosses the y-intercept once, because for the input of 0, we can only have one output. However, we can have multiple x-intercepts, and they don't even have to be real. Like I could have some polynomial that is even and looks like this, and never actually touches the x-intercepts. Now, the fundamental theorem of algebra says, well, we've got to have some imaginary ones, and if we take our graph 3D, then we'll have x-intercepts. But over the real numbers, not necessarily. And then the end behavior gets influenced by the degree, which we've looked at, and the leading coefficient. So if we have an odd degree polynomial, and the lead coefficient is positive, for example, that could be 2x cubed, our function is going to look like this, sort of our classic odd polynomial. If we have odd but it's a negative lead coefficient, maybe negative 3x cubed. There can be other stuff in there, plus 2x squared. It doesn't really matter. The end behavior is going to flip. So that lead coefficient really influences whether we're right side up or upside down. And the same thing happens with our even functions. If we're even, we end in the same direction, both up. But that's only so long as the lead coefficient's positive. So maybe that's x to the fourth plus x cubed plus x squared. Like, it doesn't really matter what else is going on. And I could throw a 3 out there to show my lead coefficient's positive, or just 1. If, however, my degree is even and my lead coefficient's negative, that's going to flip my graph upside down. And so maybe that's negative 2x to the 6th plus 3x to the 5th minus 5. I don't know. Doesn't really matter. Okay. Even functions have to have a global or absolute max or min, because even functions end in the same direction. So somehow there will be some lowest or highest point. Odd functions can only have relative ones, because odd functions will go up and down to infinity forever. The number of relative and local max and mins depends on the function. It also influences when the function increases or decreases, and a function of degree n will have at most n minus 1 turns. So if I have, let's say, x to the 5th, that's saying n, degree n is 5. If I mix in a bunch of other stuff here, and I'm just making this up so this function may not actually do what I want it to, but at most, that function can turn around, let's see, 1, 2, 3. So this could be x to the 5th. And I'm not sure I counted that right. Let me see. Let's see it. We go 1 turn, 2 turns, 3 turns, 4 turns. There we go. That's counted properly. So that is n minus 1 turns. X to the 5th, that's the most it could have. I mean, x to the 5th, though, could have no real turns. Like, we could have this, the parent x to the 5th, or it could also have, like, maybe x to the 5th minus x to the 4th, or let's say plus x to the 4th. Maybe just looks like this and only has a few turns. But at most, it has n minus 1 terms. And same thing for an even. If I had x to the 4th, let's try minus x cubed. Again, making this up, maybe it looks something like 1, 2, 3 turns max, because it's a degree 4. So you can play around with that, but that's sort of the main idea. To sketch polynomial graphs, here's my list of steps that you can do. And this also only works so long as the polynomial is factorable. Okay, you're not going to really have to sketch graphs without a computer unless it's factorable and you can end up with the x-intercepts. So the first thing you want to think about is what's the end behavior of the polynomial. That tells you, or you get that info from the degree and the leading coefficient. Then you want the intercepts, and it is important to note multiplicities. Okay, that's really important because that'll tell you whether we go through the axis or if we bounce off, which I'll talk about in a second. You're going to want to plot those intercepts, get them on the graph, and then you can sketch it based on the information above. So you use the multiplicities with the zeros, and you'll really just want to figure out like what happens when we touch and cross the x-axis, and you'll build a polynomial that meets the criteria of all this. Okay, there's some rules for multiplicity. So if a 0 has a multiplicity of 1, that means we're just going to cross through the x-axis. So let's try to see. I'll make a little sketch to the side. So that means I would just go whoop up through the x-axis. Okay. If it is a multiplicity of 2 or any even multiple, it's going to bounce off the x-axis. So in this example, which I'll put here, say I had a multiplicity of 2 for my 0, I could come down, touch the axis, and bounce off of it. And then finally, if I have 3, a multiplicity of 3, or any odd multiple other than 1, so it could be 5, 10, so on, not 10, 5, 7, 9, so on. When we interact with the x-axis, we're kind of going to snake through it. So we like come up to it, we snake on through a little bit, and that's not a good drawing. Let's try one more time. We go up to it, we kind of get close, and then we go through. And we only interacted at one point, but it has a little bit more snaky feature than the cross. Okay, so what I really suggest you do is hop on Desmos, play around with some polynomials and get a feel for this. So like our first example here we have a multiplicity of 2 for a 0 and a multiplicity of 1. So I encourage you to go plot this function, take a look at what happens with those different zeros, those x-intercepts. Here we have multiplicity of 2 and a multiplicity of 3. Go ahead and graph that, take a look at how it actually snakes through and bounces. And then we can look at a little higher degrees. Here we have a multiplicity of 4 that's going to bounce off the 0 of 1, whereas a multiplicity of 5 is going to snake through. Okay, so really the best way to do it is just to look at it, get the feel for it, mess around, make your own functions, and see what happens. So now, how would we practice this? So if we want to go through our steps, okay, first of all, I want to know the degree of this function, and I want to know the leading coefficient. So it might be useful to put this in standard form. It might not be necessary. If this term is a degree 2 and this piece is a degree 1, I know when I expand my degree is going to be 3. I also can see that my x's have no coefficient, so my leading coefficient is just going to be 1/6. So this tells me I have an odd function with a leading coefficient of 1/6 that's positive, so I'm going to look something like this with my end behavior. If I want to think about what are my x-intercepts, I can see it's going to be x equals -3 and x equals 2. But this has a multiplicity of 2. Very important, so we're going to bounce off the axis there. If I want to get even more specific, I should probably think about the y-intercept, and that's going to be influenced, if I make this into standard form, only by the constants. And so essentially I'll end up with 1/6 times 3 times -2 times -2, because -2 squared. And if you don't believe me, expand that whole polynomial and you'll find that that's all that creates the constant. We'll end up with 2 times 2, or -2 times -2 is 4, times 3 is 12, times the 6 is 2. So our y-intercept is at 0, 2. Now I want to plot these different points, so I can plot x equals -3. I'll just mark -3, 0. X equals 2, 2, 0. And my y-intercept, 0, 2. So now my goal is to build a polynomial that meets my criteria. So it has to look something like this. It has to start with negative end behavior and end with positive end behavior. We have to go through the point x equals -3 because it has a multiplicity of 1. We have to bounce off the point x equals -2, or sorry, x equals 2, because it is an even multiple. And we also have to go through this y-intercept here. So if I want to make a rough sketch of that, I'm just going to start and try. So I'll come up, cross through my x-intercept, through the y-intercept, bounce off that point, and there we go. That is as detailed as our sketch need be, and it's about as detailed as it can be without plotting a ton of points. All right, let's take a look at the next one. First thing I want to know is, what is my degree? Well, it looks like we have an x to the first, x to the first, x to the first. When I multiply this all out and get into standard form, I'm going to get x to the power of 3, which is a degree 3 polynomial. Now, again, I encourage you to multiply this out. If that's not obvious to you, just convert it to standard form and multiply it out. The leading coefficient, so this is only going to be influenced by the -1 in front. This x has a coefficient of 1, 1, and 1. So guess what? Our leading coefficient will end up being -1 because it's only influenced by the coefficients of the x terms and then the -1 out in front. Well, what does this tell me? This tells me my graph is going to look something like this. It is an odd degree, 3, so it's opposite end behavior, and it's upside down because our leading coefficient is -1. Then I want to think about what are my intercepts. So x-intercepts, we have x equals 4, x equals -1, x equals 2. All with a multiplicity of 1, meaning we need to cross the x-axis at these points. Looking for the y-intercept, again, convert to standard form if you really want to see it, but I know it's going to be -1 times this constant times this constant times this constant when it's all said and done. So I can do -1 times -4 times 1 times -2. It's going to give me +8, -8. So my y-intercept is going to be at 0, -8. All right, I've got my x-intercepts. I've got my y-intercept. I'm going to plot these points on my graph. So let's see, 4, 0. Let's get 2, 0. Let's get -1, 0. And let's get 0, -8. All right. Now, the degree is 3. The leading coefficient is -1, so we told ourselves that we have to look something like this. Start coming down and then end. We'll start with something up here and end with something down here. So I'm just going to give that a go. I'm going to try to draw, come down through my y-intercept. Some point I'll need to turn around and come back up and then come down again. Okay. You notice that's a little bit sloppy, but that's as good as it gets. That just gives us a rough sketch of what will our polynomial look like. It's got our shape, it's degree 3, and so we're happy. All righty, one more sketch to do. So here we want to do h of x. Remember, we start with the degree, start with the leading coefficient. The degree, I can see I have power 2 for my x's. Convert to standard form if you like. You will find for sure that the degree is 4. Leading coefficient is influenced by this out in front, then this 1 and this 1. So my leading coefficient will end up being 2. Though again, somewhat safer to convert to standard form. If I want my intercepts, I can say that they're going to be at x equals 3, x equals -4. Both have a multiplicity of 2, because technically I have x plus 4 twice, and I have x minus 3 twice. So that's going to mean we bounce off of both of these points. Okay. Then I want to think about what's my y-intercept. It's going to come from 2 times -3 squared times +4 squared. So 2 times -3 times 4 times, well, I should do this in different order, times -3 times -3 times 4 times 4. 4 times 4 is 16, 3 times 3 is 9, 2 times 9 is 18, 18 times 16, 18 times 10 is 180. It's not going to be so easy. Let's just do this. 18, 16, 48, 108, 16, 48, that checks out. 10 and 180 seems way too big. There we go. This is why we use calculators. And so we get 288. So our y-intercept is going to be at 0, 288. All right, our graph's going to have some weird scale to make this fit. But here we go, 0, 288. Plot my x-intercept, so x equals 3. We're going to plot x equals -4. I kind of forgot to do this earlier, but because we have a degree 4 that's even and a lead coefficient of 2, I'm going to look something like this. That's going to be what my end behavior is. And I'll probably turn around in between, but at the end of the day, that's what I have to look to graph. So if I try to do this, I can start on the left. I know I'm going to bounce off because of the multiplicity of 2. Got to come up through my y-intercept. Maybe it's a maximum, maybe it's not. We don't know. Come down and bounce off again. So here's what we would end up looking like. Okay, we're going to stay tuned. In the next video, we'll finish out this worksheet of how we actually write equations, maybe given a graph or given some different information.